You have probably looked up at a gray sky and felt that rain is simply water falling out of clouds, as if a cloud is a sponge that gets too full. That common assumption is intuitive, but it hides the actual mechanism, and it leads to confusion about why some clouds rain and others do not. How does water become droplets in the first place? Why do droplets stay suspended for so long? And what finally makes them heavy enough to fall as rain rather than mist? This can be explained calmly by following the chain from warm air to cloud to droplet growth to rainfall. The first misconception is that clouds are made of water vapor. Water vapor is invisible. A cloud is mostly tiny liquid droplets, or sometimes tiny ice crystals, suspended in air. These droplets form when warm, moist air rises and cools. Air can hold less water vapor when it is cooler. So as rising air cools, water vapor begins to condense, changing from a gas into liquid. Condensation needs a surface to start on. In the atmosphere, that surface is usually a microscopic particle called a condensation nucleus. These can be bits of sea salt, dust, smoke, or other aerosols. Water molecules gather on these particles and form tiny droplets. At this stage, droplets are extremely small, often only a few micrometers across, and they fall very slowly. Upward air currents inside the cloud can easily keep them suspended. So why do some clouds produce rain? The central process is droplet growth. Condensation alone does not usually make droplets large enough to fall as rain. Instead, droplets must grow through collision and coalescence, or through ice-based processes in colder clouds. In warmer clouds, droplets bump into one another as they move in turbulent air. Some droplets become slightly larger than others, and larger droplets fall a bit faster. As they fall, they collide with smaller droplets and merge, becoming larger still. This is a feedback process. A droplet that is slightly larger has a better chance of collecting others, and that advantage increases as it grows. Eventually, droplets reach a size where gravity wins over air resistance, and they fall as raindrops. In colder clouds, especially those that span temperatures below freezing, ice processes become important. Ice crystals can grow at the expense of liquid droplets because water vapor more readily deposits onto ice than onto supercooled liquid droplets at certain temperatures. As ice crystals grow, they can collide and stick together, forming snowflakes, or they can melt into raindrops as they fall through warmer air below. This is one reason heavy precipitation is often linked to clouds with strong vertical development, where both liquid and ice regions can exist. Cloud type and air motion matter. A thin, uniform cloud layer may contain droplets, but have weak upward motion and limited turbulence, so droplets do not grow efficiently. A towering cloud with vigorous updrafts can keep water suspended long enough for collisions and ice growth to build large particles. Humidity, temperature profile, and the availability of condensation nuclei also influence the outcome. There are edge cases. Sometimes droplets fall, but evaporate before reaching the ground, producing virga, which looks like rain streaks that vanish. Sometimes rain reaches the ground as freezing rain if it falls through a shallow cold layer near the surface. And sometimes precipitation forms as hail when strong updrafts repeatedly lift growing ice pellets through regions of supercooled water. The main idea is that clouds are collections of tiny droplets, or ice crystals, and rain forms when those particles grow large enough through collisions or ice-based growth for gravity to take over. This matters in everyday life because it makes weather feel less like a mystery and more like a set of physical steps, which is useful when interpreting forecasts or understanding why rain can change over short distances. If there are other weather processes you want explained in this same calm way, you can suggest them.